You're waking up? I hope so. It's not like you join and then you again sleep. Riddhima? Riddhima? No, you are not audible. Yeah, good morning. Pratyusha? Okay, so let's start with the pulley design. We have already done the gear blank design. The pulley design would be almost the same. The first thing that is required is the pulley diameter. From here we'll start. We'll need what is the design torque, for which we'll need what is the power this is transmitting and at what RPM this is transmitting. So we'll get the value of design torque and then we'll have to do the shaft design. Now we know that this is subjected to bending moment and twisting moment both, but bending moment data is not available. We don't know what is the length of the shaft, where are the bearings, what are the reactions, and so we ignore the bending moment part. We design the shaft only based on the torque or the twisting moment, and since we are ignoring the bending moment, we reduce the allowable shear stress also significantly. So from the shaft design, you will get the diameter of the shaft. From the shaft design, we get the dimensions of hub. So next step is hub design. Hub design is getting the diameter of the hub, length of the hub. Then depending upon the diameter, whether it is a solid pulley or a web pulley or an arm pulley, this we'll see. So assuming it is an arm pulley, then we have to go with the design of arm. The design of arm is getting the cross section of the arm based on what is the bending moment of the arm, what is the allowable bending stress in the arm, and the section modulus, assuming elliptical cross section. We check from the arm dimension, we check if beading is required. Do you know what is beading, Devesh? Devesh Jain? Devesh, are you there? No. Shravani? So as you can see, this is the pulley. We know the diameter of the pulley. This is the rim, thickness of the rim. Then this is the shaft here. We have to find out the shaft diameter or the diameter of the bore here. Then this is the hub. We find out what is the hub dimensions. This is the length of the hub and diameter of the hub. When I say diameter of the hub, it is the outer diameter of the hub. The inner diameter of the hub is same as the shaft diameter. Then these are the arms. You can see the cross section of the arm is elliptical. Once we get the arm cross section, we find out what is this beading. This is the beading. We see what is the diameter of the beading, if at all it is required. And then if this is keyed, we find out the dimensions of the key. This will complete the pulley design. Okay, should we start? Shravya, should we start?
Yes, ma'am.
Okay, take this next problem. A leather flat belt is required to transmit 15 kilowatt power 15 kilowatt power from a 1000 rpm shaft to another shaft running at 300 rpm. Diameter of the motor pulley is given as 275 mm and the center distance between the two shafts is given as 3 meters. Determine the cross-section area of the belt if the coefficient of friction between the belt and the pulley is given as 0.35. Strength of the belt material is given as 3 MPa. This is including the joint. And the density of the belt material is given as 0.9. Also calculate the initial tension by or Ti. If this initial tension is reduced by 20%, determine the power transmission capacity. What would happen if you reduce Ti? What would happen to the power transmission capacity? We discussed this yesterday. What would happen to the power transmission? Yes. With the increase in the initial tension, the difference between the belt tension, that is T1 minus T2 or F1 minus F2 increases. With the reduction in Ti, this difference would reduce and hence PR would reduce. So this kind of questions are more conceptual questions. They are not directly designed questions, but these are more conceptual questions. Somehow because of lack of time, such kind of problems cannot be taken, but if you understand the basics, you can definitely solve such problems. Yeah, let's start with the belt design first and then the pulley design. Rated power is given, give me the design power. Refer the design data book and quickly give me the values, please. Rated power. Give me the design power. Assume the service factor for the belt as 1.1. Since applications are not given, we have to assume some application. Give me the design power. All of you, please give me the answers quickly. $16.5. Okay. N1, N2 are known. Give me D2. D1 is 275. What is D2? You want to consider slip? Assume 1.5% slip. Give me D2. Pradyumna. Give me the answers. Ajinkya. Rishikesh, are you there? Rishikesh, Ajinkya, Pradyumna. Login करके where do you disappear? I don't know. Give me D2 with 1.5% slip. (902). Who is this? Richa is giving me answer. 902.9. So let me take it 903. Give me the peripheral velocity now. Pi D1 N1 in meter per second. (14.39). What is the next step? We are done till here. What is the next step? I'll keep asking you the questions unless you post it quickly on the group. Lokesh, find theta so that we get the value of T1 and T2. Center distance is known, two diameters are known. So the angle of overlap theta is pi minus d2 minus d1 by c. Give me the value of theta in radians. Mu is known. So give me T1 by T2 . 2.93, 2.97 Bharti. Richa 2.93. We'll go with this 2.93 radians. Yes. Now give me T1 by T2. Sushmita, give me the ratio of belt tensions. This is PD by VP. Ratio of belt tension. Good. Pranay and Manas are also giving answers. I thought this is only girls' day today. I am getting answers only from Shravya, Pratyusha, Sushmita, Riddhima. No. Others are also active. Good. So it is 2.78. This is T1 minus T1 by T2, right? And what is T1 minus T2? Give me T1 minus T2. Is that 1146? Pranay, is that T1 or T1 minus T2? What is 1146? Atharva?
T1 minus T2.
Okay. Give me T1 and give me T2 separately. Daitya, why you are so late? Daitya, you are joining now.
There is a power loss, so I just left off.
Okay. T2 is coming out to be 641. Others, please confirm. 1790 and 644. Yeah, so you can go with 643, 648. Likewise, this is 1788, 1789, 1790. This is T2. This is T1. What next? $641 and 230. Saurabh, what is this? My values were T1 was 1146 and T2 was 647. In case somebody is getting this. For the same value of theta, T1 by T2, my values were T1 was 1146 and T2 was 644. But if all of you are getting 1790 and 644, we'll go with this. Yeah, next step is to get the area. So area of cross section of the belt is the maximum tension in the belt T1 upon S naught minus the centrifugal tension. Give me the area. I'm still not getting answers from Aman, Lokesh, Vinay, Sarvesh. Piyush. 636 is the area. Okay. So now thickness, if we assume 0.02 times D as given in the design data book, 0.02 times diameter. This is normally the value for the leather belts. Maximum value is 0.03. You can take any value in this range. So what is the thickness? And so what is the value of B? And make sure this is less than B max. Five point five and 115. Okay, give me the maximum value. What next? Good to see all the students posting the answer. I hope all of you are solving and not just copying from whatever somebody else has posted. Next is the initial tension and the initial stress. Let's find out the initial tension Ti. The data book is referring to the formula. So find out the initial tension and give me what is the value of stress due to this initial tension. If this value is less than the allowable value of stress, we are safe, and then we go for the pulley design. One 1145 initial tension, 1144. Okay. So what is SI? The range for SI is 1.4 to 1.6 MPa. So exceeding. SI is coming out to be 1.8, which is exceeding the allowable range. So what do? We increase the area to get the value of SI is 1.6 or 1.5, little less than this. Let us increase the area. Make your area as this value of Ti upon the allowable value of SI. Let it be 1.6, or you can take it little less than 1.6. Let the value of SI be 1.5 or 1.55 MPa. This is a new area. New area is coming out to be 737 mm square. 738 with SI 1.55. Even if you take 1.6, it is okay. Even if you take 1.4, this is okay. So this completes the belt design part. Let's start with the pulley design. We have exactly half an hour for completing the pulley design part. Okay, so normally we design the larger of the two pulleys. You can design any one of them, but let's go with the larger of the two pulleys. So the larger pulley has a diameter how much? With slip, what was the diameter of the larger pulley? 903. Refer the design data book, table 15.7. What is the material that we are selecting? The most preferred material for pulley is cast iron. And what type of construction we are going with? For the diameter above 150 mm, are we going with solid web or armed construction? We are going with arm pulley because diameter is greater than 150 mm. Armed pulley. Now within armed pulley for the diameter 900, depending upon the width of the belt, whether it is up to 300 mm or above 300 mm. Kitna hai hamara? It is less than 300 mm, right? With this increased area also. For the same thickness 5.5, you can increase the thickness also to 6 mm. What is the value of B with this area? Width of the belt 134. So this is less than 300 mm. So number of arms. How many number of arms? For the diameter in the range of 450 to 1500, and for the width up to 300 arms, we are going with 6 number of arms, one set. One set. Next step. What is the next step? Shaft design. This we have already done for the gear blank. Now the shaft is designed based on the twisting moment and the bending moment. For the bending moment of the shaft, we need to know what are the loads coming, where are the bearings, what are the reactions. But since this data is not available, we are designing the shaft only based on the torque. And to compensate for the bending moment, the allowable shear stress, which is normally 70 to 75 MPa, we reduce it to 40 MPa. For shaft design only in case of assemblies, we'll always use the allowable shear stress as 40 MPa. So find out the design torque first. We have the design power, so no need to use the service factor again. Upon omega 2 pi n2, we are designing it for the larger pulley, and so the RPM of larger pulley give me the value of TD, and this shear stress would be equal to this torque upon pi d cubed by 16. Use proper units, consistent units, where this is the shaft diameter. Give me the value of TD, give me the value of shaft diameter in millimeters. I know I'm going very fast. If you have doubts, feel free to ask me, interrupt me in between. If anybody is not getting these answers. TD is coming out to be 83.5. Isn't that too small? 525 looks correct. You have to use N2 RPM of the larger pulley, 300 RPM, 525 Newton meter. Saurabh? Okay. So tau shear stress you know is 40 MPa. TD you know, gave me the value of shaft diameter. Bharti, give me shaft diameter. Tau is 40 MPa. Okay. You can refer to the material of the shaft, where normally the standard shaft materials are given with the value of, it's given on page number 111, table 11.4. Material of the shaft is normally given as SAE 1015, 1020. Again, you refer to few more pages for this material. The shear stress value is approximately 75 to 80 MPa. We take 75 to 80 MPa if we know what is the value of torque and what is the value of bending moment. But here, since bending moment is not known, so we are ignoring this value of bending moment. Because we are ignoring this, so we are to compensate for this bending moment, we are reducing the shear stress to half of the value. So assuming earlier it was 80, we are making it 40. So like we were using CV in case of gears, right, to compensate for the unknown incremental load. Likewise, to compensate for the unknown value of bending moment, we are reducing the shear stress from its original value of 75 to 80 MPa to this new value of 40 MPa. So for all shaft design, wherein you are designing only based on the torque, we will go with this value of shear stress 40 MPa. So in the shaft design, you can refer the value of tau max should be less than 0.3 times yield stress, or should be less than 0.18 times ultimate stress, and you would get the value in that range. 405 mm, this is wrong. 40, this should be good. 40.5. You have to make sure you are working with consistent units, megapascal, Newton, meter and millimeters. 40.5. If you refer the design data book, the values of the standard diameters are 40, 45, 50. So if it is 40.5, should we go with 40 or 45? "45 becomes too large, 45 becomes too large. So instead of for 40.5, it's better to go with 40. We are already considering service factors. We have increased the value of PD. We have also reduced this value sufficiently. So if this value is coming out to be 43 or anything above 43, then going to 45 is good. Otherwise, for this small change, this much 0.5 mm higher than this required standard value, moving to the 45 mm diameter makes the more material, more weight, increases the cost of bearing. Okay, so we'll go with shaft diameter 40, go for the hub design. Refer the design data book. Flat bell pulley, same table, 15.7. capital DH or small dh. What is the value given for hub diameter in terms of shaft diameter as per the design data book? Got this formula? Joel, roll number 50. Joel, you are there? No. Piyush? "49, Piyush. Ananta, if you are there, please mark them absent, 49 and 50. Roll number 52. Roll number 52, you are there? Okay, by which name normally your friends are calling you? Divakar, okay. Divakar, give me what is the value for length of the hub? In the data book? Do you have the soft copy of the data book? So I got the answers. DH is 85. LH is 60. I'm still waiting for the formula for LH from Divakar. Divakar, you don't have data book? Yeah, so give me the values, 85 and 60. So hub is done, shaft is done. Next is design of arms. So we have 6 arms with elliptical cross section. Yeah, Divakar, you are right, it is 1.5 ds. We designed the arms for bending moment because they are like long beams fixed at one end. The same table 15.7 is giving the bending moment on the arm is the difference between the belt tension T1 minus T2, which is like the load coming at the end of the arm into diameter of the pulley. We are referring to D2 minus diameter of the hub, which gives you the length of the pulley by 2. So this is giving us the radius into number of arms are n, and it is assumed for the design of arm that only half of the arms are sharing the load, which means if total number of arms are 6, then only 3 arms are sharing this total load. And so this comes out to be n by 2. And in the formula, in the design data book, F1 minus F2 is same as T1 minus T2. This is the diameter of the larger pulley, diameter of the hub by n. To explain this formula again, I am going back to the figure showing the pulley. Yeah, so this is the arm. Look at this image again. The load coming at this end of the arm is T1 minus T2. This is the difference between the belt tension. It is fixed at this end with the elliptical cross section, and this length of the arm, this outermost radius is the radius of the pulley, and this innermost radius is the radius of the hub. And so this capital D2 minus DH upon 2, this becomes the length of the arm. So it is this force into the length which is giving us the bending moment for this arm. And we are assuming, since it is not a cantilever beam, it is also attached at the other end, we are assuming that only half of the arms are sharing the load, which is also written in the design data book. So you have to give me what is the value of bending moment. Naya bending moment 165. Give me the bending moment, please. Yeah, Shraddha is giving me 165. Varuna is giving 156. Others, please confirm. All of you are getting 156 Newton meter. Okay, we go with this. Next is, since we are considering the bending moment, we have to check with the bending stress, which is equal to the bending moment upon the section modulus. Now for the value of bending moment, you have to refer to the table for the flywheel design, and this is given on the table number. Give me a sec. Table number 11.6. For getting the value of sigma, table number 11.6. This is giving you the flywheel design, and in the last row, allowable stresses in arm is giving you the bending stress in the arm for cast iron material. What is the value of sigma B given for cast iron and steady load? Pulleys are not subjected to sudden load, it is steady load. The value of sigma B is given as 15 MPa. So we are going with this value. Value of M is known. For the elliptical cross section, the very first page is giving you the value of Z, which is pi BH square by 32. Now it is elliptical cross section, and we'll always assume its width to be half of its depth. To simplify, we'll always consider its width equal to half of its depth, and so this value comes out to be h into h square upon 2 into 32. So this will be always pi h cube by 64. M is known, sigma B is known. Give me what is the value of h. And half of this h would be B. This is for the arm. So here this is B, and perpendicular to B, this is the value of H, which is double of B. Is that 60 and 30? $29.8 and 59.6. So let me take it. H as 60, B as 30. All of you are getting same answers? What is the next thing that we do? This is B, and on this view, you see this is H, which has to, the outer diameter of the hub has to hold 6 arms. So we have to see that 6 times of such width, 59.6 or 60 mm, 6 times of this 60 mm, this must fit in the periphery of the hub. So what is the periphery of the hub? That is the circumference of the hub, pi dh. And this value should be little greater than number of arms 6 into this value h for the hub. Yeah, 59.6. Take it 60 into 6, this should be 360. What is pi dh? Is that greater? IDH is coming out to be 267, and this is 360. So what do we do? Atharva, increase the diameter of what? Rajwal? Increase the hub diameter. Now there is no point in increasing the entire diameter of the hub, because then the weight is also increasing. So we are locally increasing the diameter of the hub like this, which is known as what? What do you call this local increase in the diameter of hub as? Beading. So we are providing this beading. So the diameter of the beading is equal to this 360 by pi. Diameter of the hub beading. This is 360 by pi. How much? Beading diameter. $114.6. Let me take it 115 and the same design data book, this rim thickness is also given. This thickness of the rim is for light duty and for heavy duty. Now light duty and heavy duty depends upon how much power it is transmitting. So 10-15 kilowatt can be considered as light duty. 45 kilowatt, 60 kilowatt can be considered as heavy duty, for which the thickness of the rim for light duty is 0.25 times root over d plus 1.5. Similarly, the crowning, this part, the crowning is given as 1 mm in a 100 mm face width. So depending upon what is the face width depends upon what is the width of the belt. Normally the face width is taken as width of the belt, a little more than that. And accordingly we find out what is the crown. Crown is the curvature which is given You can see in this figure, this crown ensures the belt is self-aligning. So when rotating at high speed, the moment the belt shifts away from the center, since the radius is higher here, the centrifugal force is higher, this will bring the belt back to its position. This is the effect of crowning. So you can calculate what is the rim thickness, you can calculate what is the value of crown or the crown thickness, and all these dimensions are to be given in pulley design, or when you are working with the actual design, you will need this. There is one last point, that is key. You can see here this key. How do you get the key dimensions? This key design, this depends upon the shaft design. And you can refer page number 78, table 7.5. For the shaft diameter 40 mm, what shear force, Prajwal? For key design, based on the shaft diameter, we have direct dimensions of the key given for the key and keyway. Refer page number 78, table 7.5. For the shaft diameter 40 mm, give me the key cross section. Arshini, do you have the design data book? Yes. So for this shaft diameter, which is above 38 mm and up to 44 mm, the cross section of the key is 12/8. This is the key cross section. For the keyway is the slot which is cut partially in the shaft and other half in the hub. For this 8 mm depth of the key, 5 mm should be cut in the shaft, 3.3 should be cut in the hub. What about the length of the key? Length of the key. Length of the key, it says it lies in the range of 28 to 140. What would be our key length? Look at the figure and tell me what will be the length of our key. Yes, Pradyuman is right. So this is the length of the hub. So you will be inserting a key which is equal to length of the hub. You can keep it slightly longer to protrude from one end. Slightly more, so 2 mm more than length of the hub. Or even if you take the length of the key equal to length of the hub, it is correct. Normally it is slightly projected out. So this is the cross section of the key, and then the length of the key. कितना है अपना hub length? 60 mm. Yeah, you can take it 62 mm. So that completes the belt design. Same thing is used for the gear blank design. Same thing is used for the flywheel design with arm, hub, shaft. For V belt also. So hereafter I will not be repeating this. Do you want me to stop over here or quickly revise this? It's 8:55. What do you want me to do? If you have a class immediately after this, you are free to leave. And if you can wait for another 4 minutes, let me quickly revise this, whatever we have discussed today. So we are working with this pulley design, and for the pulley design, we have to design we know the diameter of the pulley, we have to design the shaft, for which we need the design torque, power and RPM. From the shaft design, we get the dimensions of hub, then we design the arm, the beading of the hub if required, and the design of the key. So this is the problem which is given for the leather belt for 15 kilowatt power transmitted between 1000 rpm to 300 rpm. Other dimensions are given. We are left with this also. Check what happens if Ti is reduced. You know what is the relation between T1 and Ti, T2 and Ti with respect to e raised to mu theta. And when T1, T2 reduces, how PR also reduces. So this part is remaining. So from N1, N2, D1, D2, peripheral velocity is calculated, from which the angle of overlap theta is calculated. Mu and theta known, we find out T1 minus T2. PD and VP known, we find out value of T1 minus T2. And so we get the value of T1 and T2. From these values, we find out the area of the belt, thickness, and the face width, which looks good here. But when we check for the initial tension, we find out that this area is not sufficient, and we increase the area so that stress due to initial tension is well within the range. Then we start with the pulley design, and we are designing it for the larger of the two pulleys, which is a cast iron pulley. Since the diameter is greater than 150 mm, we are considering armed pulley with 6 number of arms for the width of the pulley less than 300 mm. We start with the shaft design, considering only the torque, ignoring the bending moment, and to compensate for this, we are reducing the shear stress to 40 MPa. Using the formula, we find out the diameter of the shaft as 40 mm. From this shaft diameter, we design the hub. The formulas are given in the data book. Now we have to design the arm based on the bending moment. So the bending moment is a load coming at the end of the moment, end of the arm multiplied by its length, which comes out to be the difference between the diameter of the pulley and the hub diameter upon 2. So this is the radius. And this total load is shared by only half of the arms, because these arms are not behaving like a cantilever beam, but they are fixed at the other ends also. So it is n by 2 into 2, which comes out to be n. So this is the bending moment. Bending stress is 15 MPa. Assuming elliptical cross section with width half of its depth, we get the value of section modulus as pi h cubed by 64. We get B and H for the arm as 30 and 60. We have to make sure that this 60 mm thickness is hub has sufficient place for it, and we have checked it is not. So we are increasing locally the hub diameter, which is known as beading. You find out the beading diameter. Again, refer the design data book. You get the rim thickness, crown, and then you design the key. Everything is directly given in the design data book. So this completes the flat belt pulley design. Okay, you have any questions? You are free to ask. Else we stop here.